And from the lead article of CNN, it says Hillary Clinton now leads the presidential race with national 45% support from a national sample, whereas Trump, right, had about 37% of support. And this article further said this poll, right, surveyed 1,003 U.S. adults and had a margin of error that's amount to 3.5%. So what does it mean? Okay, so this sentence is very clear to us. That's the sample size. This sentence, is also should be very straightforward. That means, it appears that more people are now supporting Clinton than, they would support, Trump. But what does this mean, right? What does it mean to say that this survey or this poll had a 3.5% margin of error? Right? What's the meaning of this sentence? And what's the meaning of this number? Why does it matter? Why does it matter? And it appears from this sentence that Clinton really is ahead of Trump. But now, if we consider this 3.5 percent margin error, does it mean that Clinton is really ahead of Trump, or should we draw a different conclusion? Okay, so this has a lot to do with how we make statistical inferences, because first of all, there's no way that the entire country has only 1,003 voters, right? But CNN, by carefully conducting this poll, that is, if CNN can draw a representative sample, then they could make some guesses about the results of the presidential race, right? Based on these very small amount of people compared to the entire population of this country, right? So that's the first meaning of making statistical inferences. That's making guesses based on numbers. But then later on we'll see, right? This, 3.5% margin of error, despite it sounds kind of has some kind of negative connotation because, well, it says error, but actually this 3.5% or whatever amount of margin of error is actually a very important piece of information that will allow us to make more concrete and accurate statistical inferences. Okay, so that's why statistics are very useful. It tells us how the presidential race is going. Okay, so now let's change the example and gradually start to understand why making statistical inferences is important and the basic logic of making statistical inferences. So imagine that you conducted a survey and you gave this 7-point scale on support of gun control to a certain population, right? Imagine you're capable of surveying every single individual in your target population. So now you're not, at this stage, you're not drawing any samples. You're surveying everybody, right, that you intend to study. So bravo. And this is, the scale that you use, right? 1 strongly opposed, 7 strongly favor. But then because, this population is huge, for example, the entirety of, all Honolulu citizens, right? That's a lot of people. So you don't have the time to really calculate the mean or any feature about this, population. Let's say, now you are interested in the mean average response, but you didn't calculate it for whatever reason, right? But then you want to have a fairly good guess about the mean instead of calculating the mean based on every single response from the population, which will be a lot of work. So you start to think, is there an easy way to do that? So let's say now you have this population, right? So you don't know, I use, dashed lines to represent, for the boundary because we don't know the exact feature of this population. For example, we don't know the mean, right? What's the mean response to the 7-point scale that we just used. But then you are being smart and say, okay, so instead of calculating the response from everybody in this population, what if I draw 3 smaller samples? Let's say each time I draw 100 people randomly, right, from the population. So this will be your first sample of 100 people, this will be your second sample of 100 people, and this will be your third sample of 100 people. So now, calculating mean responses from 100 numbers, it's much easier to calculate mean responses from, hundreds of thousands of responses, right? So very quickly then you calculate the mean response from the first sample of 100 people is 5. The second mean, or the mean for the second sample is 6, and the mean for the third sample is 5.5. Okay, now assume that your sample, the samples, are really representative. That is, the 3 samples resemble the population to a very good degree. Can you make a guess now, based on these 3 samples? What is the likely population mean responses? What is likely the mean responses for the entire population? What would be your guess? Right? Of course, you can't be exact. You can't be 100% correct. But what would be a guess that's good enough? You would say very likely, right? It's somewhere around 5.5. Right? Perhaps slightly larger than 5.5. What you can do is simply take the mean, right, of these 3 values, and it should be somewhere close to this value. And if you have this conclusion, congratulations. That's exactly the logic of statistical inferences. That is, we draw a sample from an unknown population whose features are unknown, but we do know the features of this sample. So we're now making inferences about this population based on sample statistics. That's the logic of statistical inferences. Right now, so instead of drawing 3 samples, you drew 10 samples, and their random mean are presented as follows. Right, so the mean for the first sample is 5, and the mean for the last sample, 10th sample, is 5.3. So now what is the population mean likely to be? Okay, so given this, this distribution of those values, is the population mean likely to be 5? I would say unlikely, right? Because, just by looking at these numbers, most of these numbers are larger than 5. Is the population mean likely to be 4? Again, we don't even have a 4 here. The largest, the smallest, 5. Right? Is likely to be 7. It's kind of large then, because most of the values are smaller than 6. What about 5.4? This looks more likely, doesn't it? Right? Because we do have, most of the values fluctuating around, between 5 and 6, right? One value is larger than 6, but no value is smaller than 5. And most of them are, one value is smaller than 5. But most of the values are somewhere between 6 and 5. So compared to 5, 4, 7, we should probably say that 5.4 is a more likely, is a more reliable guess about the population mean. Right? If you make this guess, then again, congratulations. You understand even better the logic of statistical inferences. That is, we're always making some kind of guesses from many pieces of information, and we'll be evaluating our confidence about a guess, right, based on sample information. Okay? All right. So far, we've been drawing multiple samples from an unknown population, or population whose features are unknown. But most of the time, right, as we said here on the slides, drawing samples from multiple drawing multiple samples from a population actually is very costly. That is, we don't usually have the time, have the resources to draw more than one sample from a population. Like the CNN poll, right? Well, CNN definitely has more resources than us, right? To draw multiple samples. But even then, even CNN, right? They don't draw samples all the time, right? It takes money, it takes time, it takes human resources to perform that activity. So most of the time, we're making guesses actually based on one single sample. Let's say here you draw a sample from the population, and we'll forget all about all the previous samples that we draw, right? So now we only draw one sample, and you'll calculate the sample mean to be 6, and that's your only sample. So what do you think the population mean is? That's a tricky question, isn't it? So you have only one sample. Now I'm asking you, what is the likely population mean? Okay. Well, the intuitive answer is, well, I want to say 6. And if we do that, then congratulations, you understand further the logic of making statistical inferences, because now we're really getting into the most common type of statistical inferences. That is, you make inferences based on only one sample. Because many times, this particular sample mean, the mean from one sample, is your best guess by being the only guess, right? So we do want to say that the population is 6, right? But we do know that the chance of the population mean being exactly 6, I wouldn't say it's impossible, but it's not very possible, right? Because we know there will be fluctuations, because we're only looking at a subset of the individuals from the population. So natural question to ask, following making our guess here is, if we say that 6 is the population mean, then what's the probability of our guess being correct? What is, how likely is this guess true, right? In other words, or to phrase this question slightly differently, is how confident are we, or are you, with your estimation based on one single sample? Okay, so that's the core question. That is the core question for statistical inferences. How confident are you? So now we can have a more formal definition of statistical inferences. So statistical inferences is essentially to make guesses about the features of a population based on sample information. So here I did not say mean or anything else. I only say properties, because you can make inferences about mean, you can make inferences about standard deviation, you can make inferences about mode, you can make inferences about almost anything, right? Of a population based on sample information, statistics that we can use to describe the sample. So this is really a very broad definition. Okay. In general, statisticians and actually most scientists nowadays, they would use two types of inferences, or they would draw two types of inferences about a population based on a sample. The first type is called point estimation, and the second type is called interval estimation. Okay, and we'll go through these two types of estimation one by one, right? So So point estimation is, as the name itself implies, right, is to provide one single estimate or guess, right, for a certain feature of the population from sample data. That's just like we say, the population mean is likely to be 6 because 6 is the sample mean, is the mean of the sample that we draw. Okay, so that will be a point estimation. It turns out that after extensive, mathematical proof, it can be shown that actually sample mean is a good sample point estimate of population mean. This sentence might seem, rather intuitive based on the words themselves, right? Well, of course, the best estimate of population mean sample mean, but mathematically it doesn't have to be the case. There are multiple, first of all, types of means. We have well, I don't want to confuse you, but just so you know that this sentence actually is based on solid mathematical proof, so that we can confidently using sample mean to make guesses about population mean. Okay, so that this conclusion is important because that will allow us, right, to say that if we have an unknown population and if you draw a random sample from it and calculate the sample mean to be 4, you will have a good amount of confidence in saying that 4, right, 4 is a good estimate or good guess about the population mean, right? So this easy conclusion is actually based on some very extensive and very creative work by professional statisticians. Okay, and similarly, sample proportion is also a good, reliable, unbiased, right, point estimate of population proportion. So proportion is very useful sort of a statistic, right? So we came across proportions all the time in daily life, right? In for example, presidential race, right? So for example, if from an unknown population you draw a random sample and it turns out that Trump has about 45% of support from the sample, then, right, this 45%, the sample proportion, is also shown by professional statisticians to be a reliable, unbiased, or good estimates of the population proportion. You're allowed to say that, with a good amount of confidence that in the population here will be, are the registered voters of the United States, right? That 45% of them would vote for Trump in November. Okay. But here's the weakness or limitation of a good point estimate. We say that it is good in the sense that it is unbiased, it is reliable, but we never said that it is precise because it can be precise, right? We know that if you survey 1,000 people from 1,000,000 people, a sample of 1,000 from a population of 1,000,000, the chance of obtaining, the population mean from the sample mean, right, for your sample mean to match, to be identical to the population mean is very, very low. So that's what we said. A point estimate is never very precise. It gives you a close enough guess, but it does not give you the true property of the population, right? So, in plain English, it simply means, right? So sample mean or sample proportion, the two statistics that we focus on here, right? Is rarely identical to population mean or proportion, but the good thing is that they shouldn't be too far away from the population mean. They shouldn't be very far away from the population proportion. They should be close, but the question is, how close, right? We can say in a scientific report or in a report to your boss, then my guess of the monthly sales is very close to the true sales number, right? Your boss is bound to ask, well, how close? Okay. And that's where, interval estimation comes in. Interval estimation will tells you how close your guess is to the true parameter or property, right? So as interval estimation, instead of giving you one single number as point estimation does, it will give you a range, right, an interval of values. It'll give you an interval, right? This is the lower bound and this is the upper bound. It gives you, in other words, two values, as interval, right, that supposedly should include the parameter that you're interested in, right? So for example, right, from a sample, we can have a point estimated population mean, and we say that is 4. But usually, right, we should supplement this point estimate with an interval estimation. So usually you will read sentence like, we're 95% confident that the population mean should fall within the range of 4 plus minus 1. That is, we're 95% confident that the true population mean will be anywhere between 3 and 5. It could be 3.5, it could be 3.9, it could be 4, right? But we're fairly confident, that is, in this case, 95% confident that it will be somewhere between these two numbers. But a question, of course, where do we get this 95% from? And what is 1? Where does it even come from? So this part is easy to understand, right? 4 minus 1, that's 3. 4 plus 1 is 5. But where does this come from? Where does this 1 come from?